Welcome back to This Explainer. I am so thrilled you're here today because we are tackling one of the absolute coolest and honestly most practical challenges in materials science. We're demystifying nonlinear modeling. If you've spent any amount of time in a lab, you know firsthand there's a massive gap between clean, abstract mathematics and the messy, unpredictable physical realities we actually measure. So today, we're going to bridge that gap. We're going to figure out how to mathematically capture the complex, underlying physics of our materials. First things first, we've got to shatter the linear illusion. When we all first learn regression, we're taught to draw a nice, clean, straight line through our data points. You know, the classic y equals mx plus b. But out in the real world, material properties almost never behave that neatly. When you expose a material to extreme heat, its thermal conductivity doesn't just drop in a perfectly straight line, it degrades nonlinearly. When you start messing with the carbon content and heat treatment of an alloy, its hardness scales in these really complex curves. The core takeaway right out of the gate is that to accurately predict physical reality, our mathematical models absolutely must bend. Here's our roadmap for today. We're looking at the limits of linearity, bending lines with polynomial regression, embracing complexity with support vector regression, diving into kernels and feature scaling, predicting thermal conductivity, and finally, choosing your modeling path. All right, section 1, the limits of linearity. Because to predict reality, our math has to be flexible. Moving right into section 2, bending lines with polynomial regression. This is our level 1 upgrade. The secret sauce behind polynomial regression is a concept called feature expansion. Now, this is a brilliant mathematical trick. We're essentially modeling nonlinear relationships by treating them as an extension of a classic linear model. How? By explicitly adding power terms, like squaring or cubing our inputs. So the really crucial point to remember here is this. The model itself remains completely linear in its weights, but it becomes nonlinear in its features. Okay, let's dive into this and trace how the math literally morphs into an actual curve. We start with a single input feature. Let's call it x1. Through polynomial expansion, we split that single input into multiple features, x1, x1 squared, and maybe even x1 cubed. We then feed those expanded features into our standard linear equation. And because those features inherently have a curve to them, our resulting output curve naturally bends to fit the data. It's just a wonderfully elegant way to trick a linear algorithm into doing nonlinear work. Let's ground this math in a highly relatable one-dimensional case study. Imagine you're working with a new steel alloy. Step 1, your primary input is the carbon content. Step 2, you measure the hardness target and observe that as the carbon increases, the hardness also increases, but definitely not at a constant rate. The gains actually start to taper off. So, step 3, to capture this physical reality, we apply a second-degree polynomial mathematical structure. We are basically asking the model to find an explicit equation using both the carbon content and the carbon content squared. And when you look at the resulting fit, it is spot on. The calculated curve perfectly traces the experimental data points. Our model generated an explicit equation for predicted hardness, and the performance evaluation shows an R-squared value of 0.993. That is remarkably accurate. It totally proves that a simple second-degree polynomial inherently captures the nonlinear physical behavior built right into the material. Which brings us to section 3. Embracing complexity with SVR, because sometimes polynomials just aren't enough. Here's the issue. When dealing with multiple intertwined variables, polynomials run the risk of wild, catastrophic overfitting. We need a totally new mindset, an upgrade to our toolkit. Support vector regression, or SVR, is built on something called epsilon insensitive loss. The psychological rule for the model is simply this: ignore the minor noise and heavily penalize the major outliers. We're shifting our focus entirely away from trying to exactly fit every single data point, and instead, we're trying to find a balanced, acceptable tolerance. Let's think about how that philosophy translates geometrically. Imagine the epsilon margin as a literal tolerance tube surrounding your prediction. Any data point that falls perfectly inside that tube, the model completely ignores it, zero penalty. It considers those points to be nothing more than expected experimental noise. The only points that actually matter to the math are the ones falling completely outside the boundary. Those outliers are called our support vectors, and they are the only points that dictate the final shape of our model. This brings us to the core optimization problem at the heart of SVR, balancing flatness with accuracy. SVR desperately wants to keep the model as simple and flat as possible to avoid overfitting. That's the complexity penalty. But it also has to account for those support vectors, the slack variables. We balance this critical trade-off using a regularization parameter called C. A really high C says, I absolutely cannot tolerate prediction errors, while a low C says, hey, keep the model simple, I'm okay accepting a few outliers. So why is this specific algorithm so amazing for researchers in materials science? 3 big reasons. First, it captures implicit nonlinear interactions without needing explicit rigid equations. Second, its high-dimensional robustness completely avoids the catastrophic overfitting we just talked about with polynomials. But third, and honestly most importantly, SVR thrives on extremely small datasets. Experimental lab data is notoriously expensive and scarce. Because SVR only relies on that tiny subset of points outside the tube, our support vectors, it absolutely excels in low-data lab environments where massive deep neural networks would just totally fail. Let's jump to section 4, kernels and feature scaling. It's time to map that complexity. Now, let this paradox hang in your mind for just a second. How exactly do we fit a rigidly straight tolerance tube through a cloud of data that is bending, curving, and heavily nonlinear? Sounds literally impossible, right? The solution here is honestly breathtaking. It's called the kernel trick. Think of the RBF kernel, the radial basis function, as a dimensionality elevator. Imagine a messy two-dimensional space where absolutely no straight line can cleanly separate or map the data. What the RBF kernel does is measure the geometric distance between points and mathematically elevate them into a high-dimensional feature space. In that new, higher-dimensional space, suddenly, a linear plane or a straight tube actually does exist. It calculates these incredibly complex implicit interactions effortlessly. But there is a massive prerequisite here, a vital caveat. Because the RBF kernel relies entirely on geometric distance calculations, you absolutely must standardize your features. Imagine mixing grain sizes ranging from 5 to 12 micrometers with a tiny porosity fraction of maybe 0.01. If you don't scale those to a zero mean and unit variance, the math will simply assume the larger numbers are fundamentally more important, and your entire model becomes structurally biased. So rule of thumb, always scale your features before running an SVR. Section 5. Predicting thermal conductivity. Let's put our toolkit to the test. Here is a real-world scenario. Thermal conductivity in a specific material decreases as porosity increases, but it also decreases as the grain size changes. This isn't just an isolated, single-variable curve like our carbon and hardness example from earlier. This represents a complex, interacting, nonlinear relationship where two entirely different features are intertwining to degrade the property. This is exactly the kind of messy reality the RBF kernel was born to handle. And this brilliantly illustrates the outcome. When we plot the experimental versus the predicted values, those data points tightly hug the ideal line with a super impressive R-squared of 0.945. The SVR model successfully captured the simultaneous degradation driven by both the porosity and the grain size variations. It managed that complex nonlinear interaction implicitly, completely saving us from having to guess the exact, perfect mathematical formula linking the two. Finally, section 6, choosing your modeling path. If you're going to take a screenshot of anything today, make it this definitive synthesis cheat sheet. Here's the breakdown. Use polynomial regression when you have isolated, single-variable nonlinearities, like a simple predictable curve, and you need a clear, explicit, empirical equation to drop into your research paper. Just be very careful of overfitting. Conversely, use support vector regression with an RBF kernel when you're doing predictive modeling on small, complex experimental datasets where multiple factors are implicitly interacting. It stably manages that risk of overfitting through its epsilon margin and its C parameter. We've seen today just how powerful these advanced regression techniques can be when it comes to bridging that gap between abstract math and physical material reality. So I'll leave you with this thought. Looking at the raw data sitting on your desk right now, which mathematical tool will you use to uncover the hidden nonlinear physics in your next lab experiment? Thank you so much for joining me on this explainer, and I seriously cannot wait to see what you discover.